Okay, starting off, I've got a couple of comments around this subject to make sure that we're all focused in the same direction. Today is a technical webinar. It's not a commercial. It's not anything about the market. It's about how surveillance drives work and how different they can be inside and how they got that way. So first off, I'd like to thank Mark Espenscheid and the entire Digital Watchdog team for bringing me forward and giving me this opportunity to speak to you. And I'd also like to thank all my friends at Seagate that I worked with for years and that are engaged in the security industry today and doing such a very good job of keeping quality high and keeping technology moving forward. And they've provided me with some data as well as a little bit of coaching in addition to the permission to actually talk about this technical subject today. This is a real nice feather in my cap. I was involved as the first surveillance video drives were released back in the day, approximately 2006, but I'm not like the guy who did it. It actually was a very large team of dedicated men and women that worked pretty hard to develop this technology and bring it forward a little bit at a time. So my intention today is to make that technology relatable and absorbable. I want you to be able to comprehend exactly what we did, in the order we did it, what discoveries we made, and what it was we were trying to achieve. I think that will be the best way for you to comprehend how the surveillance video drive is different. Next thing I want to say is there are limitations to what I can say today. We've discussed those, I know what they are. But in the Q&A, I want you to you feel free to ask whatever it is you want. Anything I can answer, I will answer. I'm going to try to be quick today and get through this material fast enough that we have time for Q&A. I think that's actually one of the most important parts of a technical presentation like this. Okay, the next thing for you to know is that as I go forward, I'm liable to fall into a pattern of saying we and you. And I don't want anybody to think that that's finger pointing or inclusive or exclusive. All I'm really trying to say with the short we's and you's is those of us that have worked inside a design center, we have comprehension about what's going on inside the drive, not just what's going on over the interface to the host. I think of those people as we. So I'm not taking credit for other people's work. I'm not excluding anybody. It's really just about those of us that were working on this technology at the time. You, who does you mean? You means anybody that utilizes hard drives and understands the basic of what they are, but may not understand the details of the internals. If you're one of those folks that has tested SV drives and tried to compare them to desktop and you found no difference, I'm also going to try to address that at the end of the presentation today and explain to you why it is you found no difference. Obviously, I can't know exactly how you tested them, but I can give you an idea of how to see the differences that are actually in there by testing in a specific way. I'll see what I can do about making that happen. All right, Mark, let's move forward to slide 4 and we'll get started. Basic operations reminder. This part's not particularly fun, but we all have to be in the same space as we start into this technical presentation in order for you to follow along with me. I'm going to be very quick. So here's a block diagram. Everything inside the dotted line is what's going on inside the hard drive. The system bus, the interface, the RAM, and the CPU, those things exist on virtually everything that is a computer. And don't forget, your phone's a computer, your car's a computer. If you've got a new refrigerator, it's a computer. So computers are everywhere, and it's true that DVRs, NVRs, and even the very earliest ones where AV drives were developed are all really computers based on their basic operation. Let's remember that the CPU can't run until the BIOS loads the operating system, the RAM becomes available, and then the interface finds the storage target on the bus. All of those basic building block principles are going to come into play as we talk a little further in how these drives are different. For this block diagram, all I really want to remind you is that the hard drive has internal processes that are mechanical as well as electronic. All the data gets encoded before it goes out to the head stack assembly and is magnetically written to the disk. The voice coil motor that moves the head stack assembly is a closed loop servo positioning function. And the disk, of course, if it's not going roundy roundy, we can't record or write anything. Okay, Mark, slide 5, please. Here's a quick overview of the mechanical interior as well as some of the key components. You can see that the good old-fashioned disks are still flat. They still go round and round. None of this basic stuff has changed since the hard drive was really designed way back in the 1960s by IBM. The recording heads have gotten an awful lot smaller. The preamplifiers have gotten a lot cleaner, a lot more crisp, and a lot cheaper. The voice coil motor has much finer control. And these days, we even have dual positioning actuators and even triple positioning actuators. The actuator assembly or head stack is an extremely precise mechanical piece. Its ability to hold the heads over a track and focus is critical. That is the one thing that is most mechanically sensitive within the hard drive. If any of this stuff has any kind of a problem, the hard drive suffers a problem and the data can be lost, or the computer can cease to function no matter what kind of computer it is. Okay, what makes the SV drives different is not a story about the interface. Although it's true that all hard drives are a computer peripheral and therefore a slave, they have to respond to commands, and that's all they can do is respond with legal commands. What they do internally can be a mystery to a lot of people, and that's what we're going to try to clean up a little bit today. I'm going to try and explain to you exactly what the drives do differently in an SV drive compared to a standard drive. All right, Mark, we'll go to the next slide. Quick reminder about areal density. When we're recording on the drive, as the disk's going around and around, we've got a bit per inch density, which means how many bits are transitioning under the head as it flies over the disk. And then we've got a tracks per inch density, which is how densely we can pack those tracks next to each other. BPI times TPI equals areal density. Areal density going up is how we increase hard drive capacity. Next slide, please. Fly height control. One more click, please. The magnetic fly height used to be established with the physical fly height. So in other words, if we wanted to make the tracks narrower, we would have to make the writer element narrower, and then we would have to fly the head lower. One more click, please. Bringing that head down closer to the media gave us an opportunity to write smaller and also to flip the bits more quickly. This is a trick that we were using for decades to get increased areal density in hard drives. However, we reached a point where it wasn't healthy to fly the heads any lower, so we had to do the whole mother of invention thing, and we had to come up with a new way. Next slide, please. What we've done here is we've decided that adding a new capability known as dynamic fly height is going to do a bunch of things for us. One click, please. By adding a piezo element between the slider body, which acts like airplane wings and determines the physical fly height, and the reader-writer element, which is attached to the back of the head and is the last piece that flies over the media, we can apply a current and we can actually change the shape of the piezo element, extending it or retracting it. One click, please. So the static spacing, as you see it shown here, that's how high the head is flying. This is by design. It's not adaptable from head to head or from drive to drive. The entire platform of a given product family is going to have a static fly height spacing. One more click, please. But if we apply current to that piezo element, we can actually push the reader-writer element down a little bit. We can also retract it upwards a little bit. What this does is it allows us to custom tune every single head to every media pairing. That also allows us to get more gain on a signal if we happen to be in a tough place in terms of pulling data back. So imagine we're at the inner diameter, we're flying extra low. We also happen to have an air-filled type of hard drive rather than helium, and we're stuck in a cache register that is at the top of Estes Park. at 8,500 foot altitude. Under those circumstances, we'd be flying extremely low, potentially even dangerously low. We can actually compensate for that now by pulling up the piezo element and giving us more ideal dynamic spacing. This is an important feature for understanding what some of the things we're going to do later. Next slide, please. Okay, we're going to very quickly touch on error correction and retries. Next slide, please. The thing we're going to talk about real quick here is a specific type of retry. It's known as ECC on the fly, error correction code. This is simply a mathematical algorithm, and it's free. What I mean by free is it can happen so fast, so dynamically, because we're going to decrypt and check the data anyway before we pass that through to the interface. We can execute this ECC on the fly without it actually slowing down the command completion times any. So here you've got 7 bits. You can see that that's like a byte. Go ahead and give me 4 clicks in a row, please. So now what we're doing is mathematically, we're looking to see which of these bits may be wrong. We've decoded the ECC check word. We've compared it to the bit that we have here, and the byte, I'm sorry, and one of the bits is not correct. So we can algorithmically go through and figure out which one it is, and we can correct it on the fly. Again, these are essentially free, and these have been going on inside hard drives for 28, 30 years. Next slide, please. There are a bunch of other kinds of retries. Hard drives have gotten very diverse and very capable in doing all kinds of things that they need to do to protect the data, shepherd the data, reconstitute the data, encode the data, reallocate the data. All kinds of things go on. The only thing you really need to know about this at this point is that the standard drive that is intended to work with computer data will have all of these retries at its disposal. And there are many, many, many pages of retries, some of which can be done multiple times. Remember the dynamic fly height? There's all kinds of things we can do. We can move just a little to the left of the data and try to read it again, just a little to the right and try to read it again. We can move closer to the disk or further from the disk. But all of these retries, all of those retries, require us to burn a revolution. We have to actually have the data going under the head before we can successfully utilize these. Next slide, please. All right, we're going to start the story now. That's the end of the boring part. We all understand that the drives are magnetic devices that have a mechanical interior as well as their programming and firmware and their electronic hardware on the PCBA. There's a lot more going on inside the hard drive rather than just executing commands. Okay, so here's the evolution beginning. It's about 1998. We're making 3 kinds of drives. Internally, we refer to them as mobile, client, and server in 1998. What do they all have in common? They're all computer drives. That's the only place drives were going. And if you remember what we talked about a minute ago, where there's an operating system, there's a CPU and RAM, there's an application that needs to be loaded, and then there are files that the application needs to open. Let's imagine we're talking about little Susie's homework. Well, little Susie can't turn her homework in if she can't print it. And if the computer can't open the file, she can't print it. If the computer can't open the file because the application can't run, or because the operating system won't run, or because there's been some form of degradation of the data within the hard drive, the whole process stops. If it's the hard drive that's not able to get it done, this is where those retry tables come in. We, at that point, have spent decades working on figuring out how to give all these capabilities to the drive to prevent little Susie from losing her homework. It isn't about how fast we could get something done, unless we were talking about the enterprise grade drives. It's more about never, ever losing data. Now you can see there's a couple of other key things here that are priorities for the 3 different types of drives. But in 1998, those are the only 3 drives that are being made. And everybody who works in a design center on the drives at that time has this one goal in mind: do not lose the data. Next slide, please. Okay, so somebody walks in and says, hey, our name is TiVo, and we're going to change the world of audiovisual entertainment. What they wanted to do was shrink down a PC, and using this tricky little graphic user interface that they figured out, as well as one of the world's first codexes, which is basically a method of taking a tuner and converting information that is being streamed as an audiovisual file into a binary stream. Then we get that binary stream recorded onto the disk and then read back off the disk. So there's this continuing writing and reading that is highly sequential. Initially, their only priorities were low cost, high availability, proper capacity. They were using about a 500 gigabyte drive. Lowest cost we had at that point in time was the desktop PC drive. So this is what we begin to sell into the TiVo market space. Initially, things go fairly well. It wasn't that hard to qualify in there, and we begin to actually sell these to the public. But we find a couple things start to happen, one of which is the field failure rates are a little higher than they are using the same drive in a computer. And we're not initially quite up to speed with why that is, because we weren't getting many drives back from TiVo, so we couldn't look into it just yet. Another thing that was happening is we discovered a mechanical problem. It's called lube channeling. Essentially, that's kind of like a water skier. When the pause buffer was being used, the head was forcibly being held long-term over the same spot of the disk. This was a result of when people leave their TiVo running, but they either go to work or they go to bed. So for the next 8 hours, that TiVo just sat there and buffered a 15-minute opportunity to rewind should somebody turn the TV on. So the head was being, again, forcibly held in a single place. Now, don't glom onto this failure mechanism. This is gone. It's long gone. Won't be back. We figured out how to kill that particular failure mechanism right away. It wasn't that difficult. But what it did was it opened our eyes. It made us realize this really is a different use case, and we needed to look more deeply into what was going on. The only other thing we knew that was happening for sure was that drives seemed to be falling behind in the continuous writing task. We weren't sure why that would be, because there was only 3 streams they could write. That's not a lot of data. That's not a fat pipe of data coming in. But for one reason or another, they were falling behind. We later found out those were command completion timeouts. I'm going to tell you how we figured that out in just a minute here. The other thing, next slide, please. The other thing that we found was that those systems were running warmer than common PCs. That's because it had the same power dissipation as a PC. It had a motherboard, had a power supply, had a hard drive in there. Everything was operating roughly the same as a PC, just that the custom application was doing something different. And the box had been shrunk so much. So the power density was high. If you have 10.5 or 12 watts that are being consumed by a PC, but the box is 3 feet tall and has 3 fans on it, you can imagine it's an awful lot cooler than something that's been shrunk down to 1/8 of that volume and has only a single 1-inch fan inside there. So power density was a problem. This slide should open your eyes a bit to the fact that you can degrade reliability by having things run at higher temperature. Important to note, that's not a hard drive thing. In fact, if you work in reliability, you know that warmer temperature is a failure rate accelerator that is accepted in every form of reliability demonstration testing for almost any product all the way around the world, from tires to popsicles to rubber baby buggy bumpers. If you're testing something for reliability, you can use higher temperatures as an accelerator. And as long as you can control the temperatures, it's easy to measure what that acceleration is. Here we can see that going from a 35°C case temperature on a drive up to a 75°C case temperature can more than cut the reliability in half. So it's not a particularly great thing to do. But it's also important to note that some drives still ran at 75C. They're not overly sensitive to temperature, but the cooler you keep them, the more reliable they are. Next slide, please. All right, here comes the evolution. There are three groups of engineers that participated heavily in the discovery of the issues and the design of the security video drive that made the security video drive come to fruition. The first group was the applications engineers. These are the folks that are dedicated exclusively to the bus. All of the commands, the command structure, the type of commands, the command timing, there's all kinds of things about that sequence of events back and forth between the target and the host that are critical. They're important. That is the entire communication path, right? But it's not the whole story, as we've discussed, because the hard drive has to be working internally before we get to that final layer of technology, which is indeed the command structure and applications engineering. The second group of folks that participated heavily was the firmware engineering team. By changing the firmware inside the drive, we were able to manipulate the way the drive behaves a little bit. We'll get into details later. The third group was the reliability test engineers. This is where you have the opportunity to determine whether you're making any progress by altering the design of the drive. So let's start talking now about how this happened and how we got into a successful area. So the bus trace analyzer, this is an appliance that's commercially available. At this point in time, 1998, 1999, we already have these in the design center. The applications engineers are using them commonly, but up to this point, they're not using them in the way that I'm going to teach you about in a minute. What we were using them for mostly then was to diagnose errors. So back in this time frame, there were multiple drive manufacturers. Those multiple manufacturers would qualify multiple chipsets to be controllers on their drives. There were also multiple chipset makers that would go on to multiple motherboards. It was a very, very large PC, server, and laptop industry back in this time frame. Because of all those chips and because of all the firmware that needed to be utilized in order to execute those chips and get them to perform, there were a lot of communications that were going on there, and problems did happen. You did come across incompatibility. You did come across issues with trying to qualify new products in various ways. Now, over the years, a lot of that's gone away. There are fewer chip makers now. The hard drive controllers are sometimes even made custom design SoCs by the manufacturer of the hard drives themselves. Compatibility isn't quite as much of an issue as it was back in this time frame, but we were using these bus trace analyzers to look at the errors and diagnose them. The bus trace analyzer is capable of showing us a bunch of other things: the type of the command, the size of the command, the response to the command completion time, whether it was an error or whether it was successful, and if an error occurred, exactly what kind was it. So we can really see some detail here. What the applications engineers did at this point in time is pretty genius. They figured out a way to set the bus trace analyzer up so that instead of stopping on error, which is the way you would diagnose an error, they allowed it to stream all of the data out the back of the device through an RS-232 port. They could then take that information and they could port it into a test PC, and they could stream the information into a file. That file could later be parsed, and then we could take specific parts of information, graph them, and we could get a visual representation on what's actually going on from the drive's point of view. Now remember, we're not diagnosing what the application's doing per se, according to the host's viewpoint. We're taking the drive's viewpoint and we're looking at what's being asked of the drive and characterizing that specific use case. And that is what began to open our eyes to where we needed to go. Next slide, please. All right, so here's some Seagate provided data. Hopefully this is going to give you a little bit of an aha moment. Surveillance video versus desktop workload. In the top part of the slide, in the gray bars, you can see we've got three categories. There's read-write activity over a 13-hour capture. There's workload characterization. There's command completion time characteristics. And then there's access pattern characteristics. As we look at desktop compute on the right first, we can see that there's more reads than writes. We can see that the workload is rather light. The drive is really sitting idle for the vast majority of its time, even if a person's actually using that computer. The command completion time requirements are kind of moderate. As long as you don't have a Windows or a Linux operating system timeout, you can go exercise all those retries that we talked about earlier, and it doesn't particularly cause a problem. The timeouts can be set within the BIOS or operating system, but for the most part, they weren't that sensitive. We typically had plenty of time. It was pretty rare that we had a timeout. And if we did have a timeout, it was usually because the drive really had a significant problem, was suffering and not able to deal with something. Lastly, the access pattern, and this is a big one. In a PC of any kind, or a computer, I should say, of any kind, a laptop, a server, even if you're using RAID, a lot of the transfer is randomly located. Randoms are kind of the rule of the day for computing functions. If we go ahead and look now down to the two graphs, we've got surveillance video workload on the left-hand graph. We've got desktop PC workload on the right-hand graph. Now remember that both of these are 4 terabyte drives. Both of these are 13-hour data captures. So this is an actual apples to apples comparison of what the drive says it's being asked to do. In the center, highlighted in pale blue, I've got a list there of the type of commands that might have occurred. We're going to look at the right-hand desktop graph first. You can see that with 62 gigabytes having been read over 13 hours and 52 gigabytes having been written over 13 hours. And look at the consistency of the sector counts. 256 sectors per transfer tells me that this is a Windows operating system. You can see that in the first 7 hours of this 13-hour trace, there's a lot more activity than there is in the second, 8 hours? Don't make me do math. I was told there'd be no math. At any rate, the first 40%, a lot of activity. The last 60%, very little activity. Also, if you can look very closely throughout that lower graph, you will see some dotted vertical lines that are orange in color. Those are read DMA commands. Those are kind of unique to compute functions. You'll never see one of those in a video transfer. Moving to the left-hand side, you can see in the lower part how much more green there is, and that's because in this particular surveillance video application, 1K sector writes is the rule of the day. Very consistent, very sequential, accessing the same part of the media for long, long periods of time. In the upper graph, you can see 284 gigabytes noted in reads, 929 gigabytes in writes, and they're color-coded for you. The green commands are writes, and you can see how those streams, a number of cameras, are there crawling across the capacity from left to right. That's going from outer diameter to inner diameter. And then you can see one blue stream. That's because we intentionally had a user set this device up so that as it was running, one stream was being read back and sent to a monitor to simulate interaction with the user. So here we've got, well, what, 4 times more data in the surveillance application than we do in the desktop compute. We know it's a 24/7 operation. So unless something significant happens with the cameras themselves, the workload is not going to change in that 24-hour cycle. And it certainly didn't change during this 13-hour capture. Now, what did this really do for us? This did several things. The first of all is it opened our eyes to the fact that it's video. Hello, it's video. What's different about video? Well, if you think about the entire concept of video, it is a format of material that is designed for the human eye to pull it in, which means the resolution and the frame rate, those two, and the pace, the consistency and the pace of the video, those are intended to emulate reality. If the video is not playing smoothly, the eye notices it immediately. And we also immediately have a function in our brain that says, hey, stop, this isn't right. I'm not getting all of it. Something's wrong. You can't watch video that's not playing right. You also can't present it in a courtroom and have somebody understand what the crime was. So sensitivity to writing down and reading back the video within specific command completion times is everything. Remember when I told you earlier that for years and years and even decades, all we were doing with hard drives as a priority was figuring out how to make them higher capacity, lower cost, and don't lose the data. All of a sudden, we got a whole new workload. Now we have to not miss writing down data because we got to be able to replay it. And we've got to replay it in exactly the right timing. So command completion times are suddenly the highest priority. The other thing that this did for us, and this is really the most important part, is it gave us this 13-hour trace of actual commands that the drive saw while it was running in this surveillance application. It's not a simulated stream. It's not a computer stream that is designed to look like a video stream. It's an actual string of commands. So in come the reliability test engineers. They took this kind of capture and they looped it on itself and created an infinite loop of actual commands that were pulled from these systems. And that can be turned into a test script. The test script can be loaded in reliability demonstration test chambers in the RDT lab. That now all of a sudden gives us the opportunity to run large numbers of drives in the actual application where we're in control. We can change the temperature, we can stop on error, we can see exactly what kind of errors we have. We can run large numbers of drives without having to buy large numbers of surveillance video applications. So suddenly we have a real world test method because of what the applications engineers provided us. Now the RDT engineers, reliability engineers, are empowered to determine whether we're making any progress. Next slide, please. Okay, so the security video drive comes out of this effort. Take a look at the things that we did first. First thing we did was we realized, okay, with that higher workload and 24-hour by 7-day-a-week operation, a desktop client drive doesn't really have the quality that we need. We needed to move to a higher tolerance head, a higher tolerance to write specifically. We needed to figure out how to manage command completion times. We needed to screen for drives that didn't mind this use case in CERT. CERT is basically short for certification testing. And we're going to talk about certification testing briefly in just a moment. We needed to use firmware so that we could manage our write cache and our read cache, it turns out. That is going to help us a lot in management of the completion times. And then we needed to actually test for reliability using actual use cases. And then we could become iterative. We can try things and see what's working. Okay. Let's talk about CERT very quickly here. In the old days, when you put a bunch of drives up for certification testing or processing, as we called it back then, all you were really doing was track average amplitude testing to make sure that all the heads were healthy and all the media had the right coercivity, so you got good signal to noise ratio and proper amplitudes. And then we would go through and we would flaw map the drive or servo track write the drive and then go back and flaw map the drive. So factory processing way back in the 1980s was a very simple process, didn't necessarily take that long. Once we got that cert processing done, we would do some burn-in. And the burn-in was basically just designed to kind of weed out some of the weaker players so that we had a filtered population that we felt was really ready to ship. But cert has become extremely technical and very complicated. There's quite a bit about cert that I can't go into because this is still an area that's highly proprietary. This is where really a lot of the secret sauce is in the hard drive industry today. But there are a few things I can tell you. One of them is this. Because we have this dynamic fly height control we discussed earlier, we have the ability to tune each head over each media to set it for optimum ability for signal to noise ratio and amplitude of signal. We also have the ability to dynamically change that in the field. We can look back at our tables and determine what was the best when we were in cert. And then we can use the retries and the dynamic fly height spacing to see if we can get any better than the way it was in cert. If we do that, then we notice there's a change. So the aging of the drive, if you will, in the field had some effect on it. The drives become somewhat self-aware. They become somewhat self-tuning. The other thing that you need to know is that there are different kinds of drives in terms of their talent. So imagine you're the team captain for the United States Olympics in track and field. You got about 64 athletes, and there's a whole bunch of different methods of running. There's long distance running, there's short distance sprinting. How come they don't use the same people for both of those two kinds of activities? Well, it's because not all people are the same. If you had an attitude of high level simplicity, it would be easy to say all people are the same. We all got two legs, we all walk bipedal, we all got two arms, two eyes, two ears, but only one brain and one heart. All people are the same. It'd be hard to argue with that. But if you look closer and you start looking for tiny differences and measuring talent in people, that's when you begin to see that people are not all the same. Simone Biles is an incredible creature. She does some things that no one else can do, but she would have been no replacement for Tom Brady in the Super Bowl. Very different talent. Well, guess what? We figured out how to look for talent in cert. So here's how this happened. We're running a large number of drives in our new RDT test script, and some of the drives are doing better with the firmware, but not all of them. We're still having some command completion time differences. As we're sitting around the table and we're talking this through, we decide, well, maybe what we should do first is screen a bunch of drives and figure out which ones are best at this kind of transfer. Let's emulate the transfer in cert and screen for the drives that don't mind it. Once we did that, and then we put the firmware on them, presto changeo. You have talented athletes in this specific kind of, let's call it long distance running for lack of a better term, and we've empowered them with the tuned firmware. When those drives get compared in RDT on this prescription script against a standard control group of desktop PC drives, now we see a large difference. Ta-da! The SV35.1 was significantly better than a standard desktop PC drive, and it was released about 2006. I was one of the reliability core team members, and I was lucky enough to go out to the field, and we went to all the CEO of all the major makers who were the kings of security video of the day, and we presented this data package, and this is how the SV drive was born. Next slide, please. Hopefully by now, what you're recognizing is this really is quite different as the drive sees it. So now what we're going to do is we're going to add another layer of technology. We're going to talk a little bit about the AI drive. So is the AI drive really any different, or are they trying to just charge a little bit more for a similar drive that's a higher capacity? Well, no. What Seagate did here is they partnered with a couple of specific OEMs that were beginning to produce real AI functionality. And we did this same bus trace analysis situation that we did before. If you look at the AI enhanced workload, you can see that it's about 15% higher workload per drive. And if you look at the graphic representations, you can see that there's a lot more activity in both the read and the write of the AI workload locality, even though these are both 13-hour captures and they're both 4 terabyte. Now, the dotted stuff that's going on in the AI there, that's a very interesting thing. Those are basically logging functions or timing marks that are being put in the data so that specific scenes are flagged as not needing to be overwritten, right, or not being allowed to be overwritten. And they're basically interaction functions with the AI itself. So as you can see, even though the sector count is the same, even though the locality is very similar, the total amount of data and the pattern of access of that data is different. So next slide, please. What we did to make an AI drive is we gave it a key feature. Seagate refers to it as tuned multi-tiered caching. They did produce a white paper on multi-tiered caching if you want to learn more about that. And basically what that multi-tiered caching is going to do for the drive is it's going to allow it to service reads without sacrificing any of the bandwidth that it needs to continue ongoing writes. That is something that is very exclusive to just the AI-enabled version of a security video application. Nothing else really works quite like that. So now what's the key with this AI functionality? Is it doing anything in a non-AI system that's going to cause me a problem, or is it costing me more when I don't really need that feature? The answer to both those questions is no, neither. All of the Seagate AI models are enabled with the AI functionality, but it's a feature that the drive can utilize as it needs it. If it doesn't need it, it won't utilize it. So if you put a Skyhawk AI in a drive that's not, or I'm sorry, in a system that doesn't have AI functionality, you're not going to see it perform that. The only way you could witness for yourself that it is there and that it works is if you were able to actually have an AI functionality, kick it in and kick it out again, and watch the actual activity that the drive does. You could measure it if you knew how to do that. All right. Drive design by use case. What I've done here is I've shown you the spectrum of the drives that are built today, from the simplest to the most capable from left to right. The Barracuda client compute drive is a basic drive, standard client, if you will. You can see through some of the specifications there that they're significantly lower capability than the Skyhawk AI, or the Exos. As you move from left to right in any one of these categories, you can see that the specifications definitely change. You do get what you're paying for, and these features are real. You can see that the tuned multi-tiered cache is not available in a Barracuda at all, but it is available in all of the industrially rated 24/7 capable hard drives. How do you know that they're 24/7 capable? The very first category, power on hours. 2400 means office hours. That's 8 hours a day, 5 days a week for the year. 8760 is the total number of hours in a year. You can see the warranty differences. You can see the workload rating goes from 55 terabytes a year in a Barracuda all the way to 10 times that in a Skyhawk AI or an Exos. That's because the platform is so much more capable. Okay, let's go next slide, Mark. All right, here's my conclusions. How are you going to make a surveillance video recording drive? Well, the first thing you got to do is you got to start with a high quality platform. There's no shortcuts. You got to have preamplifiers. You got to have controller chips. You got to have enough RAM on board, or I'm sorry, cache buffer on board. You've got to have media that has been screened and is superior media. Then you have to screen, insert to find the best drives that are naturally suited for this usage, so that you're not limiting them much when you give them the firmware that has reduced types of retries. So we're going to equip them with that custom tailored firmware. When you do those three things in the proper order, you have a security video drive. Now, there are other features that are being put into these drives. There are other recording subsystem technologies that are being developed. And what I've told you today is actually the history of how this happened. It's not necessarily 100% up to date with the contemporary. As I said, some of that is still proprietary. Key takeaways for today's presentation are that the Skyhawk AI is already artificial intelligence ready. It enables next generation features. You don't have to wait for that to come along. It's not costing you anymore. It's built into the design of the drive. It's available in 8 terabyte and higher. And the gains that have been made in field reliability through these changes over the years between the 2004 timeframe when we were starting to build the first ones all the way up to today are really quite significant. As you saw a moment ago, the Exos drive, which is the flagship, of course, that's all the way up to 2.5 million hours of MTBF. One thing I did want to mention before I go to Q&A, awful lot of folks ask me about MTBF, whether that's real at all. Is that a real specification? And the answer is yes, absolutely it is. And I actually wrote a white paper, which Mark can place on the DW website for your use. The idea behind this white paper is a simple reference on how to make sense of the reliability specifications, what they mean and what they don't mean. It's a relatively simple read, and it will help you to kind of straighten out what it is you're actually seeing when you read these specifications. Now that you understand how the Skyhawks and Skyhawk AIs came into being and how they were built, and that the enterprise drive is the most capable drive, it's got all the features built into it. Here is a quick graphic that lets you know how Digital Watchdog applies this technology. So their VMAX IP Plus and their VMAX A1 Plus, these are IP and HD over coax solutions that benefit the most within their portfolio of the tuning for this sequential transfer. They really need to be using an actual security video drive for those purposes, and they do. When you get up to the Blackjack server, now you're actually looking at a RAID striped or RAID enabled video server. The data pattern and the access pattern is a little bit different. Also, the number of cameras and the resolution and capabilities of the camera is significantly enhanced, and therefore they wisely move up to the best drive they can buy, which is the Exos family. At the very bottom, you'll see a hot link for the Digital Watchdog product selector, so you can get more information about the Digital Watchdog products and the features that they have. Also, my host, Mark Espenscheid, the Seagate host, Stefano Wildermuth, and myself, Alan Nagl, we all have our emails posted there. In case you have any follow-up questions after today's presentation, I'm happy to receive any of your questions and try to provide you with a useful and practical answer. And that should send us to Q&A.
Yes, Richard Galatas. An SV type drive in the 2.5-inch format would be great for building smaller mini PC-based NVRs. Any possibility of that happening?
Yes. There are some challenges to the 2.5-inch platform. Obviously, one of them is there's so much less surface area on the media that we don't get much capacity. And as the security industry moves forward to better and better cameras and higher resolutions, that presents a real challenge for the 2.5-inch drive to keep up. However, Seagate has produced a 2.5-inch version. It has limited capacity because they have to basically not overstress the heads and media. We don't have quite the same robustness capabilities in the 2.5-inch drives as we do in the 3.5-inch drives. So in other words, in the Exos, we've got so much robustness, we can leverage that platform to create a Skyhawk and Skyhawk AI. The 2.5-inch platform will really just have laptop drives. So we have to be kind of careful. We have to have a very robust laptop drive. And the best way they can do that is by actually detuning the capacity a bit. This makes for a little wider tracks a little lower BPI, TPI, that makes the magnetics a little more robust. Also, it should be noted that the real limitation of the 2.5-inch drive used in security video is the fact that it is still a mechanical platform, and there's a lot of temptation to put those devices, now that they're enabled with a small drive, in precarious places. So for example, if you're going to put these in a police car, a train, a bus, that's a very difficult environment for a hard drive. There's gaseous contaminants, there's shocks, there's vibration, there's large temperature swings. Um, that's not really what hard drives were designed to be able to tolerate. So that's a bit of a challenge. And so for that reason, and the fact that Seagate cares pretty deeply about having their drives be reliable and used well, not just put anywhere, right? They can't afford to have people get the wrong impression or a bad reputation because the drives are being misused. The 2.5-inch version of the Skyhawk is only available in limited quantities for key people that work with Seagate and pre-qualify it and pre-qualify the usage of it. So the answer to your question, the key takeaway that I want you to remember is there are some very strong challenges to the drive in any kind of a mobile environment, or anything that would be stressful for people is very stressful for the hard drive. So there's limited availability.
Thanks, Alan. Aaron Thomas down in the heart of Texas asked, which component of the drive enables the advanced health monitoring Seagate is able to provide? How does that compare to competitors?
The answer to that is firmware. The drive already contains all kinds of technology to understand itself and what's going on. You might be surprised to find out exactly how much drives can sense and witness and record and report on. There are some internal drive logs that only Seagate can pull out, and they can witness and realize all kinds of things that happened to the drive while it was out in the field. So because we have temperature sensors in the drives already, we have vibration and free fall sensors in the drive already, the Skyhawk Health Management is essentially tapping into some of those sensors and providing those capabilities through the interface by recognizing special commands. So the Seagate Skyhawk Health Management is essentially a reporting software that has to be designed into the system level so that it knows the commands to send and how to decode the commands it receives back. Thank you for everybody attending. I had a great time.